Welcome to Unit 4, and aren't you glad we're done with polynomials? Just kidding. Unit 4 is all about polynomials too, but polynomial functions. So it will look a little different. You've worked with functions before. Do you know what comes with functions? Graphs. Graphs everywhere as far as the eye can see. No, there's not that many, but we have 5 very important parent functions, and these are the parent functions of the power functions. I know that sounds like a mouthful, but I'm going to explain it right now, and it's really not too complicated. So we call these power functions because they're the most uh, fundamental functions we use. We use them the most often. Okay, that's why they're called power functions. But the reason they're called parent functions is because they are the most basic form of themselves. If you look at these, you'll see the blue lines are the positive parent functions and the red lines are the negative. And if you look at the function itself, you see f of x equals x squared equals x cubed, x to the fourth, and x to the fifth. So the only thing that's really changing in the functions themselves is the exponent, right? And that dramatically changes the shape of each graph. Now, some of these you might be thinking look very similar, like quadratic and quartic, and you're right, but quartic has a flatter section in the middle. Cubic and quintic, also similar, but quintic has a longer flat section in the middle. Okay, and again, the red lines are the negative versions of themselves. Okay, so everything is reversed. Okay, and you can use this handout. This is in the recordings document for 4.02. You can also find points on any graph by plugging in an x value and getting a y value. We'll practice that today. Okay, so for these, there are no shifts, transformations, nothing's moving. But throughout this unit, we will see all types of changes, things being stretched, compressed, shifted, they're going to move around. So lots of different things will happen to these lines. So it's super important you know what the parent functions look like. Because, for example, if you were tracking your fitness and you didn't write anything down, take any pictures, weigh yourself, anything for 3 months, and then all of a sudden you start doing those things, will you have anything to compare yourself to and kind of track your progress? Obviously not, right? So that's why the parent functions are so important, because we start with them and then we make changes and we can connect the two and see, did I make the correct transformations based off what the function gave me? Okay, so we're going to look at that in a minute, but before we look at transformations, let's talk about end behavior. Every line has 2 ends. I think we can all agree with that, right? And these ends continue on forever. You don't see arrows here, but they're there, okay? And the other very important thing to know is that f of x is the same as y. Write that down right now, please. F of x just means you're dealing with a function, and y means you're dealing with an equation, okay? So you could call the y-axis also the f of x axis. The x-axis is just going to stay the x-axis, okay? And that's true for all these graphs, but let's just practice one of them for now, okay? So this is end behavior, and this is the way we're going to word it. This first set of words is just for one end. So I'm going to focus on this quadratic, and I'm just going to focus on this end right here. Okay? We're going to fill in the blank. It says, as x approaches blank infinity, f of x approaches blank infinity. So as x approaches what? So basically on the x-axis, is this line, or arrow, I should say, is it moving to the left or to the right? Well, we can see it's moving up and to the left. So that's towards negative infinity on the x-axis. So as x approaches negative infinity, does the line go up or down? Well, we can see it goes up. So f of x approaches positive infinity. Now on the right, we have another end of this line, don't we? So as x approaches what? We're moving right. So that's positive infinity on the x-axis. And I might as well put positive here too. And the line is again going up. So this is approaching positive infinity on the f of x axis as well. Okay, so you're basically saying, is it moving up and to the left, down to the left, up to the right, down to the right? And you're saying it in this particular way. Now let's get to know one of the most popular functions we'll see, the quadratic parent function. Okay, and when it comes to transformations, we call the leading coefficient a. So looking at our quadratic parent function, what is a? Well, it's 1, right? We know if we don't see a coefficient there, it's 1, okay? When we see a graph, it's a parabola, right? U-shaped, okay? We see a table full of points. You can plug in any x values to find the y value to find points. So let's talk about how that works. Here I picked these x values, I plugged them into my function, and I got those y values, and you can see those points plotted. But how does a function work? They all work this way. A function is a machine, okay? Think of it as a machine. The name of this machine is f, like a factory maybe. You want to say, oh, machine f is over there. This is what it looks like. Let's see what it can do, okay? So the way functions work is you put values into the machine, those will be your x values. We also call them inputs. And you solve to see what the machine produces. Those are your y values, also known as your outputs. And now that you have a coordinate pair, an xy coordinate pair, you can graph it. Okay, so all of the work isn't shown here, but let me just show you. I have my function f. I plug in -2. Remember, if you substitute, use parentheses. And then on the left side, nothing changes. This just tells me what I'm doing. This tells me I'm using function f and I'm plugging in -2. Okay? So f of -2, well, -2 squared is 4. That's the value we see here, right? So when x is -2, y is +4, and we see that point right here. And you would follow those steps to find the rest of the points. Now, this is the parent function for a quadratic, so just notice some key features. The lowest point, also known as the vertex, so parabolas have vertexes, right? For a positive quadratic, the vertex is at the very bottom. It's also in the very middle, okay? And for the parent function, it's at the origin. Also, two very important points to know, because again, things are going to start changing as we transform and move around. There is a point at 1, 1 and -1, 1 as well. The -2, 4 and 2, 4, those are also great to know, but not essential. Okay. So we know how to use functions to find points. We know what the parent function of a quadratic looks like. Now, that was a positive quadratic, correct? So what if we had a negative? So the same exact function, just except for that one negative sign right there. How do you think that's going to affect the graph? Well, it's going to flip it over the x-axis. So you could use the table again and plug your points in there and find all the points, but it's going to flip perfectly upside down. So the vertex will stay the same. This was 1, 1, so we're going to have a point at 1, negative 1. And here this was negative 1, 1, so we're going to have a point at negative 1, negative 1. Okay, and so on. So this x-axis, in this case, acts as a mirror, and it will flip and look kind of like this. So there's our first transformation of a quadratic. But there are more, several more. One of them being when a is greater than 1. So the leading coefficient is greater than 1. Okay? Like I said before, you can choose any x values you want to put in these tables, but we're really trying to see what's going on here. So we want to be able to compare this new function, this transformed function, to the parent function. So for that reason alone, we're going to pick the same exact x values. You see those same x values in both the tables. We need to fill in the table for our transformed function. So go ahead, pause this, and take a moment to work those out. Again, you're taking every x value, plugging them into your machine known as your function, and working them out. I'll do the first one for you. Negative 2 squared. So when x is negative 2, y is 8. That's what that means. Remember, these are all ordered pairs you're finding. Okay? Well, notice what's happening here. You're multiplying everything times 2. So all of the y values are going to be multiplied times 2. So 1 times 2, 0 times 2, and then a parabola, like we said, is a U shape, and it actually also is perfectly symmetrical, where the left side looks like the right side. So this is actually going to be a mirror effect, where the vertex acts as the mirror, noticing you're going to have those same values below, okay? I'm going to just show work for 1. Let's say f of positive 1, 2 times 1, you get 2 times 1 again. So when x is 1, y is 2. Now, to find all the values, you would continue to substitute in every point, but I think you get the idea, and we have the answers there so you can check your work. So now we have all of our values, right? We have our points for our parent function and our points for our transformed function. So let's compare them and use our brains, our smart brains, to kind of predict what the graph will look like for this transformed function. Do you think it will be more wide or more narrow? Try to visualize. And if you can't visualize, that's okay. Look at the y values. These are on your y, also known as your f of x axis. Bigger y values in the new function, right? So nice work. You've now discovered that when a is greater than 1, and again, ignore the negative sign when you're thinking about this. Negative just determines is it opening up or opening down, okay? But the y values become bigger, right? Meaning the points move further away from the x-axis. We can see that shown here by the red arrows. Those points are all moving up. So they're moving further away from the x-axis. You could call that a vertical stretch. Maybe think of your arms stretching up, okay? This is a vertical stretch. So anytime a is greater than 1, that's the transformation that's happening. Ready for another one? Let's do it. What happens to a quadratic function now when a is between 0 and 1? So something like 1/2 or 1/3 or 3/4. You could write it as a decimal if you'd like, but either way, take some time right now, work this out, and find the rest of the points. Okay, so we're going to start with the first point. This time I will show all the work, but I'll do it quickly. So make sure to follow the rules of PEMDAS. And hopefully you notice that I'm multiplying everything times a half. So every y value is going to get smaller. So I think a lot of you can already predict what's going to happen. So notice this was 4, now it's 2, cut in half. So right away, I can already tell you that every value will be cut in half other than 0 because 0 times anything is 0. But let's show the work. F of -1, plug it into our function. -1 squared is positive. 1/2 times 1 is 1/2, also known as 0.5. 0 times anything is 0. I'm not going to do that work, but one thing that you should know is that your part 2 test is going to be exactly like this, okay? Where you're going to be asked to graph polynomial function and plug in points just like I'm doing here. 1/2 times 4 is 2. Okay, what do you think will happen to the graph now compared to, again, the parent function, what we started with? Well, as many of you may have guessed, when a is between 0 and 1, specifically that small window of numbers, the y values become smaller, right? Because you're multiplying them by a fraction of 1, meaning the exact opposite happens from before. All the points you can see with the red arrows, they get closer to the x-axis. We call this a vertical compression. It's like you're squeezing it down. Now, if you're thinking, well, if I put my arms out like this, I'm stretching, right? That's true, but think about it this way. It's a vertical movement. The y-axis is up and down, right? So when you're moving your arms out flat, you're moving them down. So the more flat and the more wide this graph gets, like this green line or these black lines I'm drawing, the smaller those y values get, the more pushed down it becomes, okay? And the bigger the value of a gets, the more narrow this will become, like this. And the difference table. This is different than what we've been doing, but this is something that will be on your quiz. And it's really not that difficult. It looks more intimidating than it really is. All you're doing is subtracting, okay? So you can use a difference table to find the degree of a function, right? Is it first degree, second degree, third degree? And here's how it works. You find the difference of the f of x values, so these values right here, excuse me, going down the table by subtracting from the number above it. So you, as you can see with these arrows, you do 0.5 minus 4, 0 minus 0.5, negative 0.5 minus. You get the idea. Don't forget any negative signs. Right here, there's a double negative. We need both of them, okay? So right here, I'm just showing what you're subtracting and making sure you're not doing 4 minus 0.5 or 0.5 minus 0. You're subtracting up. Okay, so when we do that, we get these values, okay? We're going to call this column 1. Those are our answers the first time we subtracted. If those values were all the same, this would be a first degree polynomial. That's how this difference table is used. But obviously these values are not the same. So we do the same thing. We subtract the value from the value above it, just like we did before, and we see what we get, okay? When I subtract them out, I get 3. 0, and 3. Again, not the same. So it's not a first degree, it's not a second degree. But you can see the third time when I subtract, I finally get the same values in that column. So that's the third time I subtracted. That's column 3. That means this is a third degree polynomial. Okay, there's going to be lots of different transformations we're going to look at for the various types of functions this unit. So stay tuned for that, but that's it for now. Have a great day.